good afternoon, and welcome to week 6. So we are past the halfway mark, and we are at about the halfway point of the material for the course, so we're on track with what we want to get done this quarter. So I'm posted midterm grades and some feedback, and I'll make some comments on that shortly, and then we'll continue talking about applications of some of this modular arithmetic business we've been doing. We'll get into crypto systems today and possibly finish that up today, and then get back to talking about logical proofs on Wednesday, which will be the next big unit of this course. So any questions up front before we kind of do a quick run through on the midterm?
Yeah, I had a quick question about like next week on Wednesday. There's a programming assignment. What is that going to be on?
It's been posted on Canvas for some time, so let's take a look at that. Let's see what we got. Thanks for asking about that, because I completely forgot about it myself. Come on, Canvas, there we go. So programming assignment due February 16th. So this is playing around with Goldbach's conjecture. And remember, Goldbach's conjecture was this assertion that every even number can be written as a sum of two primes. And 4 can be written as 2 plus 2, but for numbers bigger than 4, every even number can be written as a sum of two odd primes. So we're only going to work on this with numbers bigger than 4, because we know 4 is 2 plus 2. So your goal is to write a program that will test Goldbach's conjecture. And so you want to be able to give this program an even number and have it figure out, can this number be written as the sum of two primes? And then you're going to use this to test Goldbach's conjecture for 500 numbers, starting with 5 million. So from 5 million up to 5,998,000, so 500 even numbers. And so your program can be written in C or C++. And your submission for this assignment will be a PDF file, and the PDF file has to contain two things. I want it to first contain a clean copy of the source code for your program. So if you just cat out the contents of your source file or files, that should be the contents of the top part of the PDF, and then it should have the output from running the program, which should be 500 lines of output, each line showing that how each even number is written as a sum of two primes. Hold on, I got a chat message here. Grading questions and stuff, come by office hours and we can talk about it there. But I don't have a mechanism for making up homework assignments, but homeworks are a small part of the course grade, and having one low grade on homework shouldn't affect things in a significant way. But if you have concerns about it, come by office hours, we can talk about it. All right, so how do we do this? How do we check Goldbach's conjecture? And there's a number of ways to approach this, but the way you approach it can make a big difference in terms of how efficient your program is. So let's just work with one number. Suppose someone gives you a number like you know, 100. And you want to write this as the sum of two primes. So a really bad way to do this is to start generating primes and see if they add up to 100. That's not the approach you want to take, because that's going to take you more time than you have in the rest of the quarter for your program to run. And this would be analogous to saying, you know, well, 3 is a prime, 3 plus 3 equals 6. That's no good. 5 is a prime, 3 plus 5 is 8. That's no good. 7 is a prime, 3 plus 7 equals 10. That's no good, right? That's not a good way to find two primes that add up to 100. You can ask the same question, but you can approach this differently. I can start off with 100, and I can take my first prime, which is 3, and I can say 100 minus 3 is 97, and I can say, is this prime? And I believe it is, and so in this case, we're done, right? And now let's go on to 102, and so I'll do 102 minus 3 equals 99, and I'll say, is that prime? And it's not, because I'll run this through my prime checker, and this will be divisible by 3. So I'll go to my next prime, 102 minus 5, and I'll get 97. And I'll say, is that prime? And my prime checker will say, yeah, it is, and so I'm done. 102 is 97 plus 5. And if this turned out to not be prime, I would subtract 7. And if that was not prime, I would subtract 11. And if that was not prime, I would subtract 13. And so keep subtracting successive prime numbers from the number you're checking and see if the difference is also prime. Now, there's no point in, you know, checking 102 minus 9, because even if this turns out to be prime, this is not. And so I could write 102 as something that's not prime plus a prime, but that doesn't answer the question of Goldbach's conjecture. So here's some pseudocode. Test n. Prime 1 equals 3. If n minus prime 1 is a prime number itself, we're done. And I can print out that n is equal to prime 1 plus n minus prime 1. Okay, otherwise, I can add 2 to my prime if prime 1 is not prime. Add another 2 to it. So keep incrementing prime 1 by 2's until I get to a prime number, and then go back and check this. And if n minus that prime is a prime, I'm done. If not, change prime 1 to be the next prime number. And so this will test n, and then the main program for 5 million to 5,998, just test n. So that's how you can structure this kind of from a high level. And so your main program just calls your test function 1,000 or 500 times, right, for successive even numbers. And your test function takes a number and tries to print it as a sum of two primes. And the remaining piece of all of this is we have to be able to tell if a number is prime or not. And so you need to write a function which takes a number n and tells you whether or not it's prime. And so you can try all possible divisors from 3 up to and including the square root of n. And if if n modulo I, in other words, the remainder when you divide n by I is equal to 0, we can return 0, saying our number is not prime. If we come all the way through this and we've never returned, then our number is prime and we can return 1. So this is, you know, on the order of something that you had an assignment for, I think in 121 and probably in CSE120, depending on when you took it. We usually have a prime number program in there. And the last thing I would tell you is this business, checking to see if I is less than the square root of n. Well, you know, there's a square root function. You have to include math.h, you have to put -lm when you GCC, and you have to change n from an integer to a double precision floating point, and then compare that double to an integer and so on. But there's an easier way to do this. Instead of seeing if I is less than or equal to the square root of n, see if I times I is less than or equal to n. It's the identical check, but you don't have to do a square root, you don't have to mess with doubles and so on and so forth. So run I through odd numbers from 3 on up until I times I is bigger than n. And at that point you can stop checking and you know your number is prime. So those are different levels of the pieces. And then the other thing is I put some notes in here. And so notes, write yourself a function that tests a single number to see if it's prime. That's the one we just did. Right? Try to divide n by every number from 2 to the square root of n, or you can just test odd divisors if n isn't even. So we're only going to be looking for odd primes, so just divide by odd numbers. Rather than dividing, you can use the modulus operator. Remember, a is divisible by b if a%b is equal to 0. So that's this business over here. n% I equals 0 means n is divisible by I. The way you design your algorithm can have a dramatic effect on your program. This is what I was saying in the beginning, right? The slowest approach is to generate pairs of primes, add them, see if they add to x. The better approach is to calculate the first prime and then test to see if x minus that prime is prime. And keep going on like that. So, as in the programming courses, right, I recommend doing this in pieces. Maybe first, write yourself an isPrime function. Takes an integer, odd integer, tells you if it's prime or not. And test it. Write a main program. Print out isPrime3, isPrime5, isPrime9, isPrime25, 47, 49. Or, you know, put it in a loop. For n goes from 3 to 101, print out n and isPrime n. Or print out n if isPrime is equal to 1 and get yourself a list of prime numbers. Right? Get this thing totally working so it's completely nailed down, no questions about it, right? Give it an integer, it'll give you a 1 or 0, prime or not. And then go about doing this. This will take an even number n and print it as a sum of 2 primes. And try that. Try it with some small numbers. Convince yourself it works. Try it with some bigger numbers. And then once this is working, this is basically a one-line program, right? Just loop from 5,500,000 times, print out each of those numbers as a sum of 2 primes by using this test function, or, you know, maybe call it print as sum of primes, and that's a better name for the function. Alright, does that make sense?
Yeah, thank you.
Cool. Alright, and so that's due that's due on the 16th, 8 a.m. in the morning, right? So don't turn it in at 1 like your homework. This is due at 8 a.m. And the upload is a PDF file. And the PDF contains, you know, first all of the source code and then the output from running your program on those given tests. And as always, if you have questions with this, if you're having difficulties, if your code's not working, if you're not sure how to start it, come by office hours. If you can't ask the question in class, if it's too specific or something, come by office hours and we can screen share, and you can show me your code and we can talk about it and debug it and so on and so forth.
I have a question.
Yeah.
On the exam, are we doing those at all?
Yeah, go for it.
So on the last question, I think I missed almost all the points on it. I was wondering if you could go over that. I missed it on the homework too. I'm not quite sure how to do it with numbers.
Okay. So yeah, this one, it was a 20-point question, but I didn't take off 20 points if you did anything for it. And a lot of people seem to have trouble with this. So let's go through this. So we're trying to prove if n is odd, then 5 times n is also odd. Right? And the only thing you're allowed to use is the definition of odd, which means a number is odd if it can be written as twice an integer plus 1. And most of the mistakes that I saw were things that people did not do on their homework, and things that we talked about, not doing when we went through this in class. But then people did this on the exam, and I'm not sure where that came from. But let's look at how we can do this, and let's talk about some of the issues that came up. And so prove if n is odd, then 5n is odd. All right, this is a proposition. It's a conditional statement in particular. The hypothesis is n is odd. The conclusion is 5n is odd. And you're trying to prove if this, then that. So how do we prove if this, then that? Well, first we assume this. Assume n is odd. So here's our proof. Assume n is odd. The reason for that is that's a hypothesis. So right off the bat, there were some answers to this that did not list a series of propositions with numbers on the left and justifications on the right, but that instead said, if n is odd, it'll be 1 more than an even, and when you multiply by 5, it'll be 5 more than an even, and 5 is odd, so it's got to be odd. And that's a really great intuition, right? That's a great way to think about this and convince yourself, hey, this is probably worth trying to prove because I think it's true, right? But that is not a formal proof. And the question says a formal proof with numbered propositions, justifications, etc. That's the thing we've been doing in class every time we prove these. And you got to do it that way. That's the point of these questions, is to be able to structure that intuition that you have in a way that presents it, in this standard presentation, so that other people can read this and share your intuition, right? Understand what you see in your head. So step 1, n is odd. That's the hypothesis. That's almost always what we begin with, is stating the hypothesis. And then, since there's really nothing else we have to work with, this is usually where we throw in the definition, which for an odd number says there exists an integer, I'm going to call it k, such that n equals 2k plus 1. And that's the definition of odd. This has got to be true because that's true. We're saying n is odd. That means there exists such a k. All right, and then someone said in chat, substitution is key. And almost always when we do this, these even odd questions, we're going to write statements like this about, different parts of what we've said so far. Use this, right? We're trying to make a statement about 5n. Well, I'm just going to go ahead and do a substitution and say 5n equals 5 times 2k plus 1. And that's substitution using statement 2. And so one problem people ran into was, instead of saying this, which is a proposition, they might say this: 5 times 2k plus 1 is not a proposition. It's not a declarative statement. And when we started talking about propositional logic, I said, you've always got to make sure you remember what a proposition is. This is what I'm talking about, right? Now, I could see, you know, what somebody was doing was the steps that they would do to prove this if they were putting this together with something like this equals 5n. But just writing 5 times 2k plus 1 or 10 times k plus 5, those aren't propositions. Okay, if I have an equality, this is a proposition. I'm claiming that this is equal to that. And it's true because I've already proven that n equals 2k plus 1. And so I can replace that with the n because of substitution, and therefore I can say without any doubt 5n is equal to this thing over here. So this is a true proposition. That's why it's true. The next thing that people ran into was kind of jumping the gun on the conclusion. So next I would see something like 2k plus 1 is an integer, therefore 5n is odd. Well, stating that this thing in parentheses is an integer does not prove that 5n is odd. 10 is an integer. 5 times 10 is not odd. So the simple fact that this 2k plus 1 is an integer does not say anything about whether this is even or odd. The only time we've said something about something being even or odd is when we can write it as 2 times an integer plus 1, or 2 times an integer. But writing it as 5 times an integer, that doesn't tell us anything. So we have to do something to try to get it into the form of hopefully 2 times an integer plus 1. And so this is where we start doing algebra. And so we can expand this. 10k plus 5 equals 2 times 5k plus 2 plus 1. That's algebra. Algebraic manipulation applied to proposition 3. And all I've done is taken this right side, 10k plus 5, and that's, 10k plus 4 plus 1. And this is the kind of intuitive part that you need to look at this and, look on your ignore section. 2 parentheses something, close paren, plus 1. How can I write this as twice something plus 1? Well, subtract 1. How can I write 10k plus 4 as twice something? Oh, write it as 2 times 5k plus 2. All right, now we can go ahead and we can make the observation 5k plus 2 is an integer. That's properties of integers. The fact that multiplying and adding integers by integers leaves you with integers. And now you can make the observation, hey, 5n is 2 times an integer plus 1. 5n is odd. And that's the definition of odd, taken together with 4 and 5. And that's what we were trying to show. So that's the end of the demonstration. So that's a way to prove it, and those are some of the pitfalls that pop up along the way. Another thing that pops up sometimes is somewhere up in here, people state 5n is odd, and then they write 5n equals 2 times j plus 1, and they do some other stuff, and then at the end they say 5n is odd. Well, I cannot write 5n is odd unless I've proven it, or I'm taking it as a hypothesis. And it's not a hypothesis, it's the conclusion. So if I write 5n is odd, I've got to justify it with something that I've already done. And if I could do that at this point, I'd be done, because that's what I'm trying to show. So don't list the conclusion until you've proven it. It's the thing you're after, but you don't get to put it as part of your proof. If you do, all you're showing is that if 5n is odd, then 5n is odd. And that doesn't prove this. right? If I'm rich and famous, then I'm rich and famous. That doesn't prove I'm rich and famous. So it's got to be, you know, step by step, and each step has to follow from the previous steps, or it has to be, you know, a hypothesis that we're given as, you know, you should take this as given and then try to show the conclusion. All right, does that make some sense?
Yes, thank you.
Okay. And so while we're thinking about proofs, let's go ahead and look at number 5. That was the other proof question. This was very much like some of the questions from the book. So we're given D, B implies A, B or C, D implies not C, and then we're asked to demonstrate A. And you can write this in vertical form if you like. And I think direct, indirect proof, kind of similar amounts of work here. But, you know, if you eyeball it, it's like, well, we've got a D up here, we've got a D implies not C. We can definitely put those two together. We've got a B or C. Well, we can't really put that with this. To use this with direct reasoning detachment, we'd need to have B. And if we had B, this would get us A. But there's nothing here that immediately says we're going to have B. But let's put the D and that implication together. So I'll state D. That's a hypothesis. I'll state D implies not C. That's a hypothesis. I'll put those together and get not C. That's detachment from those first two. Well, now I know C is false. And remember, you know, eye on the prize, I'm trying to prove A. This is the only thing that says anything about A. So somehow I've got to prove B. This is the only other proposition that mentions B. So let me write that down, B or C. That's a hypothesis. Well, this says B could be true or C could be true. Or both, but at least one. How can I get from there to knowing that B is true? And the answer, yeah, the answer is right there, right? I've already proven C is false. So this says either B or C is true. This says C is not true. Logically, that means B has got to be true. It's either Monday or Wednesday. It's not Wednesday. It's got to be Monday, right? Those are the only days we have class, Monday or Wednesday. And if it's not Wednesday, it's got to be Monday. And so there's a way to put those together to prove B, and that's called disjunctive. Is that disjunctive simplification? I think so.
Detachment.
Detachment is...
Oh, no, disjunctive simplification.
Yeah.
I think.
So disjunctive simplification says if you know one of these is true and you're given one is false, it's the other one that's got to be true. So this is disjunctive simplification of 4 and 3. And now once you have B, we're ready to put that together with this. But we have to state this first as part of our proof. If B, then A, that's a hypothesis. And now we can put those together and get A, that's detachment. 5 and 6, and that's what we're trying to show. And if you wanted to go indirect, start off with negation of A. Well, if we have not A and we have B implies A, that's a hypothesis. We can use indirect reasoning to say, hey, B must be false. Right? If B, then A, but A is false, so B has got to be false. That's indirect reasoning. and then B or C is a hypothesis. But B is false, this means C has got to be true. That's, again, disjunctive simplification. Well, D implies C. Sorry, D implies not C. That's a hypothesis. Well, if we put these two together with indirect reasoning, if D is true, C is false, but C is true, D must be false. That's indirect reasoning. Between 5 and 6. But we're also told D is true, that's a hypothesis. Well, we've proven D is false and we've proven D is true, that's a contradiction. 7 and 8 contradict each other. Therefore, statement 1 must be wrong. Therefore, A must be true, and that's what we were trying to show. So that's like one extra step, I think. All right. So other questions on the exam?
Give me one sec. Oh, I missed question 2.
So question 2 is looking at
Oh, this one.
at quantifiers, and so we're given for all x and z p of x. All right, that's what we're given. We're asked to find which of the following is not equivalent. And so part A is really how we would say this in spoken language, right? For all integers x, p of x is true. That's really what this means. So A is definitely equivalent. So we definitely, that's not going to be our answer. B is an example we actually worked through in class, which was related to negating these quantifiers. This says, for every x, p is true. And remember this says for some x, p is false. Well, these are opposite of each other. For all x, p is true. For some x, p is false. So it can't both be true. If there is an x where p is false, then we cannot say for all x, p is true. And if we know that for all x, p is true, then we cannot say, there's some x where it's false. Right? This is like saying, I'm happy every single day. Well, except there was that one day I wasn't happy. Right? These contradict each other. So to say, I'm happy every single day means there was not any day that I wasn't happy. There's never an x for which p fails. So this is exactly equivalent to statement B. There does not exist an x in z such that not p of x. Alright, so that leaves you with C or D. One of these is not equivalent. And if you put down either of those, you got at least 5 points, because you were able to eliminate these two things that were equivalent. But it's subtle trying to figure out which of these is true. But there was a homework question way back when related to stating that there were an infinite number of integers, and the idea that for all x there's a y that's bigger than x. And that's what's going on here now. So fix in our minds, for every x, p of x is true. Okay, what does this mean? This means the following propositions are true. Right? for all integers, p of x is true. So any integer that I think of, p of that integer is true. All of these things are true, and all the ones that I didn't write, and all the ones I might ever write. Okay, so we got that in our brains. P is always true. Okay, so what does C say? C says, for all x, p is true, or p of x plus 1 is true. So this is saying if you pick any integer, either p of that integer is true, or p of the next integer is true. D is saying for any integer x, p of that integer is true, and p of the next integer is true. Okay, so if this is what we're given, then both of these things are true. But do both of these things necessarily tell you that this is the case? And so let me give you an example. Let p of x be the proposition x is even. So this is certainly not true for all x p of x, because not every integer is even, right? We have odd numbers. Statement C, though, says for every integer x, p of x is true, or p of x plus 1 is true. In other words, for every integer x, x is even, or x plus 1 is even. Well, this is a true proposition. For every x, either x is even or x plus 1 is even. So C cannot be equivalent to this original proposition. Whereas D says, you know, for any x, p of x is true and p of x plus 1 is true. They both have to be true. And so C is the correct answer here. C is the one that's not equivalent to this. But like I say, if you said D, you got half the points anyway, because you eliminated two possibilities correctly.
So the answer was C and D, or just
The answer is C.
Okay. Yeah, that one confused me.
That's the deliberately subtle one. But it was
way too many points.
But it was basically a 5-pointer. All right, well, while we're in here, two sets, 1, 2, 3, H, J, K, M. So the union, you put them all together. That was fine. The intersection was null. I didn't plan that to be null because it made some of this a little freakier than I had planned. But the intersection turned out to be null. I mean, I thought it would make the intersection easy, but I forgot about the power set part. So intersection is null. A take away B. Start with A, throw away any of these that you find in B. Well, none of these are in B, so A take away B is just this. And most people got that. And then the intersection is the empty set. So D was asking for the power set of the empty set. And this should be a set, and it should contain all the subsets of this. And remember, the empty set has exactly one subset, which is the empty set. So the power set is actually this. Or you could write it as this. Right? But it's a set containing a single set. And that's subtly different from just the empty set itself.
Which one was that? Because I think I missed that one.
This was 1D. So the power set of the empty set is a set containing the empty set. It's a set with one element.
That's what I missed.
I think you docked me points because I didn't have it in brackets.
Yeah, because this is different from that.
Okay.
So this is something with no elements. This is something with one element. And we did this when we talked about power sets. We said, what if you take the power set of the empty set, and that's the power set of this thing. And that's a set containing all the subsets of this, which is the empty set and the set itself. And then I think we did it one more level out, and then I said, I'm not going to go beyond that. And then A union B, take away B. Well, put these things together. That's the set of all of these things. So all 7 elements. And then you take away these 4, and that just leaves you with A, 1, 2, 3. And then 3, I'd actually meant this to be a conjunction, an and instead of an or, because I didn't want it to look as weird as it ended up looking, but P implies Q or not Q, so here's P, here's Q, here's P implies Q. And remember, the implication is true except when the hypothesis is true and the conclusion is false. So this is false, all the others are true. And then if we make a new column for not Q, that's just the negation of this column. So true, false, true, false. And then the thing we're asked to make the truth table of is P implies Q or not Q. And so we want to take the or of these 2 columns, and it turns out that's true in all cases. So there's the truth table. And then it says write a different proposition that's equivalent to this. And most people came up with good answers for that. You could have simply said true, but that might feel risky. But you could make, you know, some other combination. Some people did things like, you know, P or not P. That's always true. And other things like that. At least one person, I think, said something like this. And that's also a proposition that's logically equivalent to this, right? Because it's always true. And then let's go ahead and do number 4. So match the following to the reason why it is true or false. So I did not ask you to prove that these were true or false or give examples of them. I wanted you to match each of these statements to the reason why it's true or false. So all fish swim, I swim, therefore I am a fish. Okay, so this statement says if you're a fish, you swim. This says I swim, therefore I'm a fish. Right? Well, that is not a true statement, right? Because, you know, suppose all fish swim. That's believable. And I do swim. I love swimming. But I am not a fish. This would be a different kind of course if I was. So this is some kind of fallacy. And it's the fallacy of affirming the conclusion, because this all fish swim is the statement, if you're a fish, then you swim, and then you affirm the conclusion. So this is the fallacy of the form, you know, fish implies swim, swim, therefore fish. Right, so that's affirming the conclusion. So the answer for A was B, fallacy of affirming the conclusion. Alright, second one says, if I study for class, I will pass. I did not pass, therefore I did not study. So let's do that. If I study for class, then I will pass. I did not pass, therefore I did not study. And so is this a law of logic? Yeah. This is what we call indirect reasoning. I think if you said contrapositive, I gave you credit for it, but this is indirect reasoning. Contrapositive is, you know, not P implies not S. Indirect reasoning is the law of logic, which says given this and this, we can conclude that. And so the answer for B should be G. But if you said contrapositive, I gave you credit for it, because that's basically what's being used here, is a fact of contrapositives. Alright, and then C says, if one studies for class, they will pass. So if you study, you will pass. You studied for class, therefore you will pass. And that's, you know, rule number 1, that's good old detachment, direct reasoning. So that would be F. Next one, if it's sunny, I'll go for a run. If I go for a run, I'll get hungry. Therefore, if it's sunny, I will get hungry. And I think everybody nailed that as chain rule, right? S implies R implies H, therefore S implies H. You're just chaining those together. And then E, I'm going to study computer science or art. I am not studying computer science, therefore I'm studying art. And that's the one we use in question 6. That's disjunctive simplification. So you're told that one of these is true, the first one's false, the second one has to be the true one. So that would be H, disjunctive simplification. All right, other questions?
All for now, for me.
I am curious to know, like, was it enough time across the board for everybody in class?
I did alright-ish, but I finished in like 20 minutes. I thought it was actually super short.
So I think it depends on how quickly one can work.
I feel like this one right here, this question right here, the one that we're looking at, I'd assume takes the most time. This was what took me the most time. Word problems in general, kind of.
Yeah, this kind of problem can be tricky because, you know, theoretically each of these you have to compare to each of these and think about it, and by the time you get to the fifth one it's all probably starting to sound the same. One approach to these kinds of things is to try to get rid of the words, right? Try to change this into something with propositional variables, and then, you know, if you have an idea of what this is, see if you can find something that matches it. But I mean, I had a few students who, you know, commented on the exam that they were out of time, particularly at the last question. And so that was a factor for some people. I didn't expect people to finish, you know, much under 50 or 55 minutes. I expected people, for the most part, to need the full amount of time to do these. But as I've said in class and in feedback comments and so on, right? If there's a sense of a time issue in any of my classes, right? Definitely come and talk to me. And there's ways to, you know, officially set up accommodations for extended time. Some of those take time for those processes to go through. But at least having a conversation about it lets us talk about strategies for maybe how to optimize time on a test, or ways to work on, you know, homework problems or things like that with a mindset of a timed exam. And there's more practice problems that I can point people to try to get, you know, a little faster with doing these things and so on. But, you know, different people work in different ways, and sometimes it's just going to work better to get extended time on tests. And there's generally ways to make that available. So one more time, you know, if anybody has concerns about that, definitely get in touch with me and let me know, and we can talk about it. And my goal is, you know, to have students be able to show their understanding of the material on the exams. Right, that's the goal, because, you know, the exams and the homework, programming assignment, that's your grade.
I thought both of the exams were excellently timed.
Okay. The other thing I'll say in this course in particular is, you know, there's usually some curving that goes on at the end. And so don't panic about your grade at this point, right? If there's a source of panic, it should be if, you know, if you look at this question and you have no idea what a set is or what this means, and you feel like you've never seen it, right? Then there's some material to go back over. If you're writing up proofs and you don't understand this idea of, you know, why I say you should have an ordered set of propositions, and a justification next to each one that explains why each one follows and so on. If that's something you feel like you're seeing for the first time or you've never quite understood, let's definitely talk about that, right? Because there'll be more proofs in this course, and there'll be proofs on the final, and you know, the sooner that we get things squared away as to, you know, how to put together a proof and such, the sooner you'll be able to get more practice with it and get in good shape for future assignments, including the final. And so let's definitely have a conversation about that if you're feeling unsure about any of the material. And I think that's far more important than worrying about the grades at this point. Because the final is cumulative, and it's another opportunity to sort of show your understanding across, you know, the entire set of material for the course. So we should be looking forward rather than back, I think. All right, other questions? All right, so let me organize some stuff here. Let's go ahead and do a 5-minute break. It's a good transition point. Let's do a break, and let's come back in. We'll just come back at 2 o'clock, and we'll try to wrap up number theory and applications of number theory. Alright, we're back.
You ever thought about Lego brick tolerances?
Lego what?
Lego brick tolerances?
They are very tight as far as I know.
Yeah, you can put a Lego brick that you bought today on a Lego brick from 80 years ago.
Yeah.
It fit perfectly.
Yeah,
That's
it's pretty impressive. I mean, you can like 3D print Lego shaped blocks, and they don't work at all like Legos. They are really resilient. They have great material properties, and I guess they don't change over time, which is pretty cool. Some quality engineering there.
I mean, you could think about it. Even if one generation of Legos sticks on the next, you could easily have them be unfitting after a couple of generations.
Oh yeah, definitely.
But like, they all still fit perfectly.
Yeah, it's impressive. Wow. And I just got a note that a friend of mine from college passed away.
Oh, that's too bad.
Yeah, it is, because he was my age.
I'm sorry, man. That's
Yeah, thanks.
Condolences.
Huh, that's too bad. Yeah, Jay. I'll tell you about him later. Anyway, alright, it's one of these days. Alright, so applications of number theory. So we talked a little bit about parity on Wednesday. So this idea of transmitting data over a noisy communication channel, and sometimes your bits will flip, and so you want to send, a message like this, and instead when it gets received, it ends up being this. And we had this idea of a parity bit. If we could insist that the number of bits sent is always, number of 1 bits is always even, we could tack an extra bit onto the end. And so in the case of our data being transmitted correctly, we'd see 1, 2, 3, 4, that's an even number of ones. But when a bit flips, we'd see 1, 2, 3, 4, 5, that's an odd number of ones. We'd say, oh, there's a parity error. So, so that's one approach to that's one approach to error handling, and it's a summation of bits, and you reduce modulo 2. And then I mentioned things like error checking and correcting codes that work the same way, and creating hashes like an MD5 hash, which is a big operation you perform on the bits of a stream of data, or the bytes, and then you do some of these modulo reductions and so on. You end up with a number that uniquely identifies or more or less uniquely matches to the original input that you were processing. And so if the input changes, you get a different output from this function. And so this idea is mimicked in other applications. So one example is universal pricing codes. So when you say again?
I have a question.
Yeah.
So there's like MD5 hash, right? And people use hashes for tons of things. You hash your password, to store them and whatnot. There's a lot of different hashing algorithms, but there's like MD5, and then they have like a bunch of them that are just like the same, but like with higher integers. I don't remember what they're exactly called.
Mm-hmm.
And then there's ones that are salted. What are those salted? Do you know?
Salting is a whole different matter.
Okay.
My understanding of salting is if you have a way to change one thing into something else, every time that you change the same thing, you get the same thing on the output side. And so let's say you're encrypting passwords, right? You can't look at an encrypted password and figure out what the password was. It's a one-way operation. But if you find passwords on two different databases and they encrypted to the same jumble of stuff, you know that those have the same password. And so without knowing what the password is, you understand that, you know, this person's Facebook account and their Twitter account have the same password. So you salt the password before you encrypt it. You throw in some random stuff. And then even though you're encrypting the same password, the encrypted versions look different. And it's just another measure of protection against somebody being able to make deductions about you know, common passwords across systems.
So each system will just have a different salt that they'll add at the end?
Yeah, it'll actually vary, like, it'll be a different salt each time that this is done. So it won't just be per system, it'll be like per password.
Very cool.
Yeah, it all gets really, like, clever and pretty quickly beyond what I can easily grasp myself. But, you know, if you take a crypto course, you'll dig into all that stuff. There's a lot of really elegant techniques and mechanisms that are used in security, and a lot of pretty impressive things that are done to try to get around this, right? Different ways of running exploits to try to crack passwords or you know, decrypt information or things like that, and it's pretty fascinating across the board. All right, so UPCs, universal pricing codes. So when you buy a product from the store, you pick up a product in the store, it's got this little barcode on the back. And let me see if I can find something here. No commercial products in my immediate vicinity, but you know, these little codes you see on the back of things. Oh, here we go. Thank you. All right, there's a UPC. So 13700812000, and so, you know, this goes through a laser scanner right now to pick up the pattern, and then, you know, it tells the cash register what this product is. But when these first came out, these codes were typed in by hand, right? Or if it doesn't scan for some reason, you type it in by hand. And the problem, the potential problem is, you know, if you type this in and you mess up one digit, this might ring up as, you know, a TV set, and the person's going to get charged, you know, $600 for a thing of Ziploc bags. Or, you know, someone buying a TV set, you might type in the wrong code and it thinks they're buying a pack of gum, and they get their TV for, you know, $1. So since we're using these numeric codes to represent, you know, a product, it would be nice if it was somehow immune to these kinds of errors, because key punch errors are really common. Well, not really common, but, you know, they can happen. And so the way this works, so this code, and I'm a little suspicious of it, but I think it's technically a 0, and then a 13700812220, and then I see a 0 at the end, but I'm suspicious of those two. Nope, that's right. Okay, so this is a product category, so that's a general, you know, one-digit grouping. And then this is the manufacturer. So this is presumably, you know, for Hefty or whoever owns Hefty and so on. And then this is for that manufacturer. This is unique to the actual product. So it's really an 11-digit code, and then this is a check digit. And the check digit is generated from these, and it's generated in such a way that if one of these digits is wrong, the check digit will be wrong. And it's also generated in a way so that if two digits are swapped with one another, if you type an 18 instead of an 81, the check digit will change. So yeah, very, very much like ISBN. In fact, ISBN is going to be the next example. So the way this works is as follows, and it's a pretty simple algorithm. So if we call this x1 through x11, x12, so we use the following formula. We take 3 times x1 plus x2 plus 3 times x3 plus x4 plus 3 times x11. So we add up each of these digits, and we multiply the first, the third, the fifth, and so on by 3. And then we finally add x12. Maybe we don't add that. Alright, so we take this and we reduce it modulo 12. Sorry, modulo 10. Alright, so add up the first 11 digits weighted like this, reduce it modulo 10. And let's call that C. And then if C is not equal to 0, if C is not equal to 0, use 10 minus C. And this is our check digit. If C is equal to 0, our check digit is just 0. So you take these 11 digits, add them up, and this is basically, 3 times x1 plus x3 plus x5 plus x7 plus x9 plus x11 plus, and then just the sum of the evens. So we can add up 3 times the odds plus the evens. So let's pull these out. So the odd ones are 0, 3, 0, 8, 2, and 0. So 0, 3, 0, 8, 2. So 8 and 2 is 10, and 3 is 13. So this is 13. And then the even ones will be 1, and 7, and 0, and 1, and 2. So 1 and 7 is 8, plus 1 is 9, plus 2 is 11. So 3 times 13 plus 11, this will be 39 plus 11 is 50. 50 modulo 10 is 0. If this was anything other than 0, we would subtract it from 10. But since it's a 0, we just leave it as 0. That should be the check digit that we get. Thank you. And sure enough, that's what the check digit was. That was that last piece of the UPC code. And if you swap two of the, if you change one of these, it's likely to change the sum. If you swap two of these, then instead of multiplying the 8 by 3 and adding 1, we would have multiplied 1 by 3 and added 8. And so this will catch 100% of single-digit errors, and it'll catch 90% of transpositions. There's a few cases where you could transpose two numbers, and you get the same check digit. But 90% of the cases, it'll catch this. And so you key in all 12 digits, or you scan all 12 digits. The system runs this check, and if the check digit doesn't match, it knows something is wrong. And it'll beep, and you have to rescan or re-enter. So credit cards do this also. If you type in a random 16-digit number for a credit card, chances are it'll tell you it's invalid. And it doesn't do that by contacting a bank. It does that because not all 16-digit numbers can be credit card numbers. They have to satisfy certain characteristics like this.
And then you have Amex. That's weird.
Yeah. So that's universal pricing codes. ISBNs are similar. And there's a bunch of different types of ISBNs, but ISBNs are these codes you see on books that numerically identify the book. And there's different versions of this, but one version, so this is a 10-digit code, and so you do sum from I equals 1 to 9, and it's position weighted. So you take the ith digit and you multiply by I, and you add all of those up, and you reduce the sum modulo 11. And that gives you a check digit, and if you end up with 10, that's written as an X. So when you reduce mod 11, you'll get something between 0 and 10. 0 through 9 is just a digit, 10 will be an X. So sometimes you see an X at the end of an ISBN, that's check digit 10. And so this is also very robust. It catches errors, it catches transpositions. And again, it's just the idea that, if you're typing these things in by hand or scanning them or something that is error prone, it will give you an added measure of protection against just randomly putting in a number and, it gets correlated to a different book. Instead, it's likely to come out and say that's not a valid ISBN. And then you have to enter it again. And proving or demonstrating that, these things work, that they will catch errors, that this will catch 90% of transpositions and so on, it all comes down to doing, these matters of modular arithmetic and looking at modular systems and things like that. And we're not going to dig into details of that, but, it's just be aware that this is one of the application areas where all of this stuff kind of comes into play. Alright, so let's talk a little about cryptography. And this is a big subject. This is something you can do a whole course in at a university, and these are usually fun classes, I think. If you like math at all, cryptography is usually a pretty good course because it's a lot of math. But it ties into a lot of computer science and a lot of the things that we're doing, the past week in this course. And so what's the basic idea of cryptography? You have a piece of information that you want to send to somebody, and you don't want other people to know what this information is. So we have one way that's pretty simple of doing that we've used for a long time. It's called an envelope. You put your letter in an envelope and you send it, and presumably nobody else will see the contents of that message except the person that you sent it to. And so this is why we, use envelopes instead of postcards. But, there's certainly nothing stopping somebody who intercepts that envelope from opening it up and reading it. So the security of the message is based on the security of the communication channel. And putting a message in an envelope and dropping it in the mailbox, technically pretty secure, right? Depending on other things. But, typing in an email and sending it, absolutely not secure, right? Everybody has access to that information if you're just sending a plain text email. And so if the communication channel is not secure, you have to assume that any message you send can be intercepted and read. And so the idea of cryptography is, let's make the message itself meaningless to other people, so that the person we're sending it to can understand what I'm saying, but somebody else won't be able to. So it's kind of like, you know, having a secret language you and your friends use when you want to talk. And so this is...
joke around watch lists from our WhatsApp messages.
Oh, yeah.
WhatsApp's better than regular messages.
Yeah, and I mean, it's probably just me, but I assume there's like no security in any of that stuff unless I'm encrypting it myself, right? So, you know, you send a Gmail and there's some level of encryption, or you chat on Zoom and there's some level of encryption, but, you know, I didn't write the software, I haven't reviewed the software, I have no reason to believe that any of that information is secure. And so even if I'm, you know, using Gmail or you know, something like that, if I wanted to send secure information, I would encrypt it myself and arrange, you know, an encryption strategy, decryption strategy with the person I was communicating with. And that's just kind of, you know, what you do. So this has gone on for, you know, at least thousands of years. And so there's a very early cipher called a Caesar cipher. And I don't know for sure, but I assume that, you know, this was something that Julius Caesar might have actually done. And this is a version of what's called a shift cipher. And the idea is, you know, you want to send a secret message, like hello. And so you arrange with your person, hey, when I send you a message, I'm going to add 3 to every letter. And so the H becomes a K, the E becomes an H, the L becomes an O, and the O becomes an R. And so, you know, I put this in an envelope and I hand it to a courier, and the courier starts carrying it across the countryside. And if someone intercepts the courier and steals this message from them, they can't tell that I was saying hello. They just see, you know, gibberish, and they're like, oh, you know, Nick lost his mind, right? But if the message makes it to my friend, they see this, and I already told them, you know, my encryption key is +3. So what do? They subtract 3 from each letter, and they can read the secret message, hello. Okay, that's a real simple cipher. Cipher just means, you know, a way of encrypting information.
I thought the Caesar cipher was one where they wrap it around a rod or something.
Well, I think that's the same thing. Because if, for example, you know, if I wanted to encode the letter Z, that would, how do I add 3 to Z? Well, I wrap it around and I come back to C. And so you could make a little tool for encrypting things by having, you know, your original alphabet here and your shifted alphabet down here. And you can put these...
It's called the Skytail cipher. Okay.
Okay. And so you can put these together by you know, putting them in circles and have a pair of concentric rings, and look at one letter and look at the letter next to it to see what the letter corresponds to.
Yeah, that's what all those, what is it? Yeah, decoder rings. Yeah, there you go.
Yeah. So that's like a decoder ring.
Game that used one of these encryption methods. All the game files were just like regular .NET XMA files, but all the bits were had like the number 55 added to them or something.
Oh, cool.
So I just went through and subtracted 55 from all of the values in each of the files, and it decrypted them to complete normal. I was very shocked at how like little effort went into it at all.
Awesome. Yeah, so when I was a kid, you'd buy Captain Crunch and there'd be a decoder ring inside sometimes, and it wasn't this fancy looking, but it was still really cool. And it, basically had a pair of dials you could turn relative to each other. So this one is set so that, you take H and you add this amount to it and you get a U, and you take I and you get a V, and so on. And so if you wanted to write hello, you just look up what the corresponding letters are here. And then your friend would set their ring, the same way, and they would read the ciphertext letters on the bottom, and they'd find the translated letters on top. And so that's a pretty simple way to encrypt messages. But if you don't know what's going on, you get a message like this, and you think, oh, I'll never figure that out, and so it's some measure of protection. You might use it for your diary when you're a kid, but it's not what the NSA is going to use. So a few things to mention here. There's plain text, which is sort of the original message, and then there's ciphertext, which is encrypted, or modified to make it unreadable. And when you start with plain text and you change it into ciphertext, that's called encryption. So encryption is turning it into gibberish, and turning the gibberish back into plain text, that's decryption. And I'm pinning down those terms because if we think about this process, here is the plain text, here's the ciphertext. To encrypt, what did I do? I used my secret password +3 to change this into that. To decrypt, my friend used the same secret password, but instead of adding, they subtracted from these letters to get back to the plain text. So the encryption key was +3, the decryption key was -3. And this is the first observation I want to make about a Caesar cipher. It's what we call symmetric. Symmetric means the encryption key and the decryption key are closely related to each other. Now, to turn the message into ciphertext, I need the encryption key. I need to know how I'm going to modify this into that. To turn it back into plain text, my friend needs the decryption key to turn it from ciphertext back into plain text. But in reality, right, if I know the encryption key, I know the decryption key, and vice versa. Encrypting is just add 3, decrypting is subtracting 3. All right, so this.
I know that
Go ahead.
they just I'm not sure how recent. I'm sure I think pretty recent, like in the last year or two, they finally solved the last
Zodiac Killer.
Zodiac Killer cipher.
Oh, really?
2020.
Yeah. Okay. Yeah. So 2 years ago. Yeah.
No, I didn't know that.
Yeah. When I last read about it, it was unsolved, and then I was reading about it just a bit ago, and they solved it. It's pretty crazy.
Huh. I'll check that out. If you want,
Definitely the mind of someone a little insane.
if you want to dabble in something related to that, check out the Beale ciphers, which are pretty much considered to be a hoax at this point. But supposedly this person buried $40 or $50 million worth of treasure, and somewhere in Virginia, and the location of it is encrypted, and people have been trying to decrypt this message for over 100 years. And there were 3 messages. One of them has been decrypted, and that describes the treasure. But the other 2, including the one that describes the location, nobody's been able to crack yet. But that sounds like maybe something similar.
Yeah, this one just talks about how he killed people.
Yeah, that's a bummer.
Yeah, not quite as.
Yeah. All right, so this is a symmetric cipher, and we're going to come back to this later when we talk about public key crypto, which is asymmetric. But the Caesar cipher is the first example. If you know how to encrypt, you also know how to decrypt. And if you know how to decrypt, you know how to encrypt. All right, so so that's one cipher, and this is not a very secure cipher, right? For one thing, you only have 26 possible keys. So you can just try the 26 possible ways to decrypt, and most of them will give you stuff like this, and probably only one of them will give you stuff like this. So you take your text, you decrypt it, you know, with all the possible keys, and you run it against the dictionary, see if there's actual words in there. And as soon as you find a few words, you probably found the right decryption key. So super not secure, right? So a slightly harder version of this is a substitution cipher. And this is the Caesar cipher is really a substitution, right? You replace I with V and J with W and K with X, but they're all, you know, related to each other. This is just a certain number of characters beyond that. This is the same number of characters beyond J. This is the same number beyond K. So a substitution cipher, you would do something like this. And you would just say, well, this is going to go to an E, this is going to go to G, this is going to go to B, this is going to go to W, this will go to Q, this will go to X. And you just kind of randomly say, okay, here's my cipher, right? And this is my encryption key. So I take my plain text and I just look up the replacement letters for this. And then how do I decrypt? Well, my decryption cipher looks like this. And I'd probably reorder it so it's alphabetized, but all the information for decrypting is contained in the information for encrypting and vice versa. So if you know one, you know the other. And this is also not very secure. It's not very secure because of the characteristics of the English language or any language. For example, in English, the letter E is the most common letter. And so if we, you know, have a piece of encrypted text, we do a frequency analysis and we find the most common letter. If we find that H is the most common letter, it's a good bet that H is coming from the letter E. And whatever the least common letter is, if we find the least common letter, maybe it's an X, we can say, okay, well, that's probably a Z, if Z is the least common. And this frequency of distribution of letters is very, very well behaved for large amounts of text. So if you have a big enough piece of text, you can crack a substitution cipher just by doing this frequency analysis. And that's not too hard. All right, so here's another thing we can do. We can do a transposition cipher. So here's a message. This is fun. And we can define a way to scramble these letters together. And so my encryption might be something like this. I'm going to break my input into blocks of 3. And I'm going to do the following rearrangements. I'm going to take the first letter and put it in the third position. I'm going to take the second letter and put it in the first position. And I'll take the third letter and put it in the second position. So first goes to third, second goes to first, third goes to second. First goes to third, second goes to first, this goes here, first goes to third, I'll put a space at the end, second goes to first, and there's a space. So this is fun became hit is space FSN space U. And so this is different from a shift or a substitution. But it's still fairly easy to crack with frequency analysis. For example, TH occurs fairly often. QU doesn't occur very often, but whenever Q occurs, almost always a U comes after it. And so you can look at frequencies of different pairs of letters, and based on frequencies of occurrences, you can start to make some guesses about, you know, TH looks like this. And you can do things to try to figure out what the grouping size was, and once you've done that, now you can start to look for pairs of letters, or, you know, short strings of letters that make words that occur commonly, if, and, or, things like that. And so this is pretty easy to attack. But again, it's also a symmetric cipher, because the decryption basically says, you know, well, to encrypt, I'm going to take the first letter and put it in the third position. To decrypt, I'll take the third letter and put it in the first position. I'll take the first letter and put it in the second. I'll take the second letter and put it in the third. So to decrypt this piece of ciphertext, I'll take the third letter, put that in the first position. I'll take the first letter, put that in the second position. And I'll take the second letter, put that in the third position. And there's the first three letters of my message. Alright, so these are all symmetric ciphers. The problem with a symmetric cipher is the following. If you want to do something like online commerce, let's say you're Amazon, and you want people to send you credit card information. Now, you know you can't just send it across, you know, an open channel, because anybody can intercept stuff that's sent on the web, especially if it's Wi-Fi, right? You just need a radio receiver. So you need your customers to encrypt the information they send you. But if I tell my customers, hey, here's the secret encryption you're going to use when you send me your credit card, well, anybody that I've told that to automatically knows how to decrypt those messages. And so unless there's a different encryption key for every customer, right? If two people are using the same encryption key, either one can decrypt the other person's message. And it's not feasible for Amazon to send every person on the planet their own encryption key. Actually, they'll probably do that someday. But, you know, that's a huge overhead. And if you have to, you know, do that to do business with someone online, you're not going to do business that way. So the challenge here is the fact that if you know how to code your message, how to turn it into ciphertext, you also know how to decode it. And if multiple people are encoding messages, you can start intercepting those messages and decoding them. And that's a problem. So this problem has been solved. And the solution to it goes way back a number of decades. And how far do I want to go down this? So, here's the heroes of our story. So you can tell this was like the 60s, 70s, right? Yeah, I wish that was me. Ralph Merkle, Martin Hellman, and Whitfield Diffie. So three mathematicians, computer scientists. I've actually met Ralph Merkle, and he's interesting to talk to. He's doing a lot of interesting stuff with nanotechnology these days. I met him in the 90s when he was starting a company called Zyvex, and he's gone in some interesting directions. So this is you know, a few decades ago. There were no CRTs for the most part, so everything was printed out on this fanfold paper, which was nice because you had a hard copy, you know, of everything you did, but it took a lot of trees. So Merkle, Hellman, and Diffie. So Hellman was a teacher at Stanford, and he was thinking about cryptography and computers and sending information from machine to machine and trying to do it securely. And he understood this basic problem that, you know, if you know how to encrypt information, you also know how to decrypt it. And so if a lot of people want to send encrypted information to the same place, and they all share the same encryption key, they can decrypt each other's messages. And he wanted to know if there was a better way to do encryption, if there was a way to do something like this. Here's plain text. And here's your encryption password, which turns you into ciphertext. And then that ciphertext, you use some kind of decryption password to go back into plain text. But to do this in a way that if you knew this, you could not figure out that. If you used 3 to encrypt, you did not know that -3 was the way to decrypt. If you use this transposition, you know, 1 goes to 3, 3 goes to 2, 2 goes to 1 to encrypt, you did not know how to decrypt. So this was the idea of an asymmetric cipher. And he realized that if we wanted to do encryption that we could, you know, use for e-commerce, we needed this asymmetric mechanism. All right, so Diffie, person here on the right, so he did his bachelor's in math at MIT in the mid-60s, and he was interested in cryptography. And so he started traveling around the country. He was giving talks. He was talking to different crypto researchers, and he got to IBM, and people told him about Hellman and said, hey, you should check out this person at Stanford. He's been, you know, talking about similar things. So he called up Hellman and, you know, told him who he was and what his interest was and asked if they could meet. And he gave him a appointment for 30 minutes. He said, come by my house, you know, and I can give you a half hour. So he showed up and they started talking, and they never stopped. They talked until dinner. They had dinner together at the house. They kept talking. He left like close to midnight, right? And it was just, you know, kindred spirits. They were both kind of on the same wavelength. So around the same time, Ralph Merkle was an undergrad at Berkeley, and he was doing computer science. He was taking a security class, and he was looking for a cool project to work on. So it's like, you know, SLPs at Clark. He had to come up with his own project and then work on that. And so he thought it would be cool to try to come up with an asymmetric cipher, right? And he talked to his professor, and the professor told him his idea was, quote, terribly muddled, and said, you know, you can't work on this. And so like any good student, his response was to drop the class and start working on this on his own. And so he pursued this as a pet project. Don't drop your class if you don't like your SLP, though. So he had some experience with this from his own kind of inspiration and insight. Got his degree, went on to work on a master's degree at Berkeley, and mid-70s, he was talking to some people about his crypto ideas, and somebody mentioned, you know, you should go talk to these people at Stanford, because you sound an awful lot like them. And so he went to Stanford, and he met Hellman and Diffie, and the three of them hit it off. And they started, you know, brainstorming on how to make this whole asymmetric thing work. So later that year, Hellman published a paper, and it was sort of the mathematical foundation for what we call public key crypto today. This idea of being able to encrypt information in a way that doesn't let other people decrypt the ciphertext. And he published a paper, he gave some talks, and his colleagues got worried because they understood that this was a totally different level of security. And they understood that this meant that other people could send messages that in particular the US government would not be able to decrypt. And so some of their colleagues contacted NSA, National Security Agency, and NSA contacted Hellman, and conversations ensued, and in the end, the algorithm for doing this encryption was classified as a munition, which is an instrument of war. And instruments of war are very closely governed by the federal government. For example, you're not allowed to export it. You're not allowed to disseminate it. And so he had planned to go to a conference the following year and present his findings there, and he was basically told by the government, you cannot do that. If you do that, you'll be considered exporting munitions, and you'll be arrested and tried for, you know, all these crimes and so on and so forth.
A bunch of punks.
Yeah. And so this was a pretty tense period in the history of all this. So this was October 77, right? And Stanford had basically said, you know, we'll support your decision to present at this conference. If you're arrested, we will defend you, right? We'll pay for attorneys, that kind of stuff. If you're found guilty, we can't pay your fine. We can't go to jail for you, right? It's your choice. And he decided he was going to do it. His students were advised not to go to the talk. And they were early in their careers. They didn't have tenure, that kind of stuff. The risk for them was much greater. They originally said they wanted to do this anyway. And then in talking to their families, they decided, okay, we're not going to talk. We'll sit on the stage, but we won't say anything. And the talk came. It was at Cornell. He presented his results. He presented the papers from the two students. The government was there, and nobody was arrested, and nothing happened. And that was basically the end of the government monopoly on secure encryption systems. And so
they just didn't do anything?
They didn't do anything, yeah. I mean, and basically, you know, the cat was either out of the bag or was going to get out of the bag very soon. Because it's really hard to clamp down on information like this. And you know, I mean, it's mathematics, you know. It's mathematical equations. It's an algorithm we're going to go through today or Wednesday. And, you know, it's very hard to secure and keep secret an algorithm. And this is one of the other things about cryptography. You can never really assume that your algorithm is secret, right? So, you know, I was always inventing codes when I was a kid. Well, take the letters and add them up and then multiply by 7 and then divide by this and take the remainder. And all this stuff that just turns it into jumble, you know. You can never really assume the algorithm is secret. And, you know, in particular, if you've got this algorithm encoded in your machine and you're running this piece of software, you can throw it in the debugger and trace through it and see exactly what it's doing. So algorithms can't be secret. The secret has to be in the key itself. But there was a period of time. Anybody here remember using Netscape? This is like way back. Give me a thumbs up for Netscape. Or a woohoo. Yay. All right, we got some. Excellent. So Netscape was, you know, you'd get CDs sometimes in magazines and stuff like that. But there were two versions of Netscape. If you were in the United States and you promised not to, like, give this to your friends from other countries, you could use the strong encryption. And it had a longer password that you could use. If you had a copy you were using outside the US, you would have to use the weak encryption. And it was like a 56-bit encryption algorithm or something. And the government actually mandated, you know, that you could only use the stronger encryption, you know, within the U.S. borders. And you couldn't send information outside and all this kind of stuff. And it was kind of goofy, you know, and that's kind of gone away now. And encryption is pretty, you know, open market at this point. But, you know, the stuff still comes up. You get like the Clipper chip and all that kind of stuff where people want backdoors in encryption algorithms, or they want, you know, strong encryption on HDMI ports so you can't take the output of your DVD player and record it, you know, and stuff like that. So this is still, you know, a very political area. But we made it through, you know, this question of can you, you know, discuss the mathematics behind these algorithms without breaking the law? And the answer is yes. So this lecture will not be illegal. If things had gone differently, you know, maybe it would be.
Maybe we'd all be treasonous.
I know, right? And so go ahead.
On the topic of saying things being illegal and whatnot, there's a video on the internet of this guy saying about offing the president of the United States. And basically he says how it's illegal. There's a bunch of other stuff. And he went to Supreme Court for it and was arrested, and he's now dead. I don't know how old you would be, but I don't know, kind of related in a little bit.
Yeah, yeah. Yeah, and you know, freedom of speech is a relative thing. So, you know, the classic example in law school is you can't yell fire in a movie theater, even though that's, you know, freedom of speech. Well, it's not, right? And freedom of information, right? So you can post what you want on the web with some exceptions, right? You don't want to post instructions for a bioweapon, right? Is that freedom of speech? Well, yeah, freedom of speech is not absolute. And same thing with, you know, making threats or slanderous comments or things like that. So yeah, this is why I'm not a lawyer. So 1977 also saw Rivest, Shamir, and Adelman, whose initials give us RSA, which was a public key crypto system that was used for a long time. And there's other versions of this also. And so RSA is the one that we're going to study. Or we're not going to study it. I'm just going to wave my arms around and talk about it for 20 minutes or so. And I think maybe we can get through this, but let's see how far we can get. So RSA is a public key crypto system. It's a system where we have an encryption key and a decryption key. And knowing how to encrypt presumably does not tell you how to decrypt, which means I can announce to the world, hey, when you want to send me secure information, here's how you encrypt it. And everybody can do that using the same key, but if they intercept other people's messages, they still can't decrypt it. And so this ties into, you know, a lot of foundational things in cryptography, signing things so that people know it's actually coming from you, doing passwordless login. So if you set up an SSH protocol on Linux, right, you can log into another machine and it doesn't ask you for a password, but it's not sending, you know, a password insecurely over the open channels and so on. So let's see if we can get through the basics of this. And, you know, I'm not going to ask you details of this on an exam. What I want you to know is that, you know, there is this notion of an asymmetric cipher versus symmetric, and you should know what the difference is. Symmetric cipher, if you know how to encrypt, you know how to decrypt. Asymmetric, if you know how to encrypt, you don't know from that how to decrypt. But I want to just sort of wrap up today by showing you, you know, at least a high-level view of how RSA operates, because it nicely takes all the stuff we've been doing for number theory and brings it together. So we start with a pair of large primes. P and Q are large primes. Large meaning a few hundred digits each. Okay, so, you know, whatever that is, skrillion. So large numbers. Both prime, and we set n equal to p times q, so that's their product. So n is a really big number, and e equals some large number relatively prime to p minus 1 times q minus 1. So e is some number that shares no factors with p minus 1 times q minus 1. And our encryption key is the pair n comma e. So if somebody wants to send us a message, we give them n and we give them e. And they will use that to encrypt the message to us. The reason this works is that to decrypt, I need to know p and q. And if p and q are 100-digit primes, then n's going to be, you know, roughly a 200-digit number. And right now, we don't have a way to factor 200-digit numbers. You can know what this number is. This is public domain because it's in the encryption key. But knowing that does not tell you what p and q are. And knowing e does not tell you what p and q are. So the one-wayness of this is the fact that, you know, to encrypt, I can tell you n and e, but that does not tell you p and q. But as the person who came up with the encryption key, I know P and Q. I can use those to decipher. And that's the whole security of it, the whole asymmetric part, is that you can't get P and Q from N. When that changes, all the encryption we use breaks. So if quantum computing happens to, become real tomorrow, no more online commerce, right? No more secrets for a while. But right now, this is pretty secure. All right, so to encrypt our message, let's just assume we're using letters A through Z. And we'll take our message and we will write it as a series of 2-digit numbers. So if we want to send the message, cab, well, this is letter 3, this is letter 1, this is letter 2, and, cab at noon. So there's A is 0, 1, T is 20, and I think is 14. O is 15. I might be off on these, but work with me, right? So you take your message and you turn it into a big long integer, okay? And we break it into blocks so that, whatever block size we use, this number is going to be smaller than n. So if n is, 200 digits, we break it into blocks of basically 100 letters. And so, we chunkify it, and here's the first number that we're going to encrypt, and then here would be the second number we'd encrypt, and so on. And the encryption is done on blocks, so all we need to know is how do you encrypt one of these messages, one piece of the message. So a set of letters, which is, very large, but guaranteed smaller than n. Alright, so to encrypt, our ciphertext is just m raised to the e modulo n. So take your message, take the letters of your message, turn them into integers, form a big long integer m. Raise that to the power e, reduce it modulo n. That gives you a big long integer, that's your ciphertext for this message. Alright, so someone wants to send me this message M, I give them N and E, they perform this calculation, they send me C. C is encrypted. So how do we decrypt C?
Using log or something?
Using something, and this is going to be pretty quick because we only got about 15 minutes. I got a video on this too where I actually do this for a short message, and I can point you to that if you're interested. But this is just kind of like convincing you that it's plausible. So if you know P and Q, which I do because I am the one who's created this encryption key. So if I know P and Q, you can find a number D such that D times E is congruent to 1 modulo P minus 1 times Q minus 1. You got to kind of trust me on this one. But this comes out of Euclid's algorithm. And the idea that E is relatively prime to this. And so E and this will have a greatest common factor of 1, which means that we can solve this equation. So we can find a number D that when you multiply by E gives us 1 more than a multiple of P minus 1 times Q minus 1. So DE is congruent to 1 modulo this. So there exists an integer K such that DE equals 1 plus K times P minus 1 times Q minus 1. That's what this means. It means DE is 1 more than a multiple of P minus 1 times Q minus 1. So C, the ciphertext raised to the D, is equal to, our ciphertext is M to the E raised to the D, which is M to the D times E. which is m raised to the 1 plus k times p minus 1 times q minus 1. Just substituting. So if we take the ciphertext and we raise it to the d, we get something congruent to this. This is modulo n. Since n is equal to p minus q, and this takes some demonstrating, but it's not very deep. This will also tell us that c to the d is congruent to m to the 1 plus k times p minus 1 times q minus 1 modulo p, and c to the d is congruent to m to the 1 plus k times p minus 1 times q minus 1 modulo q. Did I mention this is not on the exam? So this is just for recreation. So ciphertext raised to the d is congruent to this thing modulo p, and also congruent to the same thing modulo q. All right, assuming, and this is a pretty minor assumption, assuming the greatest common divisor of m and p is equal to 1. And that's almost always going to be true, right? It's very unlikely that your message that you've created is going to share a common factor with this very large prime p, right? If it does, it would have to be equal to that prime or be a multiple of it, right? So this is almost always a safe assumption, and if it's not, you can add, an extra space in the message or do something like that. So we're going to assume that the greatest common divisor of m and p is 1, and that means we can use Fermat's little theorem. So Fermat's little theorem says the following. It says m to the p minus 1 is congruent to 1 modulo p. And same thing over here, m to the p minus 1, m to the q minus 1 will be congruent to 1 modulo q. Right, so that's just Fermat's little theorem. Well, this up here, c to the d is congruent to m to the 1 plus this kind of thing here. We can expand that out. So we can take this and say c to the d is congruent to, well, this will be m to the 1, which is m, multiplied by m to the k times p minus 1 times q minus 1, which is m times, and if we rearrange these, it will be m to the p minus 1 raised to the k times q minus 1. And since this is congruent to 1, this is congruent to 1, this is just congruent to m. And this is mod p. And you do the same thing, you can show that c raised to the d is congruent to m mod q. And then you make the observation that the greatest common divisor of p and q is 1. They have no common factor because they're both prime, and presumably they're not the same prime, because that would be a really bad choice. And now you take the Chinese remainder theorem, and the Chinese remainder theorem in this case tells you, since c to the d is congruent to m mod q and c to the d is congruent to m mod p, that c to the d is congruent to m mod p times q. And remember, p times q is n, so c to the d is congruent to m modulo n. And our message was chosen to be smaller than n, and so if we just take c to the d and reduce it modulo n, that will give us back our original message. So the functional punchline is, right, pick a pair of large primes, multiply them, pick some large number relatively prime, that pair n and e, that's your encryption key. You give that to somebody else, they take their message, raise it to the power E, reduce it modulo N, that's the ciphertext. The only way I can decrypt this text is to take that message and raise it to the power D. Right? And the only way to find D is to know the original primes P and Q. So if I know the original primes P and Q, I can find D. I take their ciphertext, raise it to the D, that gives me back the original message. But if I don't know the original primes, all I know is N and E, it's more or less impossible to find those original primes, at least in a reasonable amount of time. And so I have no way to get those primes. I don't have a way to find this decryption key. So that's a lot of hand wavy and a little bit of math. And like I say, I have a video on my channel from last year, I think, maybe 2 years ago, where I go through this, you know, more slowly, and I actually build up a message, pick a pair of primes, find an E, and then actually go through the process of turning a short message into the encrypted text and then decrypting it. And, you know, I think it takes about 45 minutes to do that for a really simple example, so I don't want to do that in class. But if you're intrigued or interested in it, let me know and I can point you to that. But that's an example of a public key crypto system. And like I say, the main takeaway I want you to have is just the fact that these things exist, and they have this fundamental characteristic of, you know, knowing how to encrypt. It does not tell you how to decrypt. And so Amazon, for example, would tell the world, hey, when you want to send your credit card, use this encryption. And everybody can do that, and these ciphered messages are flying all around the open web, but you can grab these from other people and you cannot decrypt it because you don't know the secret decryption key. So that's an asymmetric cipher. All right. Questions, comments?
It makes me want to take a cryptography class.
Do it. Definitely recommend it.
It makes me want to not take a cryptography class.
Don't do it. Definitely don't do it. Yeah, I took a crypto class from a math department at Duke, and it was really fun. And I got to look at quantum cryptography for a project, and that was really cool. WSU, you can take crypto as a computer science class, I believe, and it looks pretty interesting. And you go into, you know, a much deeper aspect of all of this stuff, and you actually code it. And when you code something, it really kind of helps you understand what's going on too. So that's always a good possibility. All right, so Wednesday we're going to shift gears and go back to talking about mathematical proofs. We're going to talk about mathematical induction, and that's going to be the big takeaway from this course, and that's going to tie in nicely with recursion, which we're starting to talk about in CSE215 with recursive algorithms for trees and such. And so we'll see a lot of parallels between what we're doing in here for the next week or so and what we're doing in 222 data structures. So I'll post some homework for Wednesday. It'll be a chance to do some of these number theory operations and concepts, finding a greatest common divisor, seeing when two things are congruent, modulo something, doing modular exponentiation, things like that. So that'll be a chance to sort of put in practice some of the things we've talked about. So I'll post that for Wednesday. We can talk about it Wednesday or, you know, in office hours if you like. All right, we are at 3:10. I'm done here. Have a great afternoon, and I will see everybody next time.
Good afternoon as well.
Thanks.
Thank you. Have a good day.
Thank you.